All good? Yeah. Okay. So, welcome everyone. Good morning, good afternoon, good evening for those who will see the recording of this one. I'm really happy to have today with us Mike Rayo from Ohio State University and deliver the first of a longer series of webinar focused on resilience engineering. In particular, I am Riccardo Patriarca, and I'm an associate professor at Sapienza University of Rome, Department of Mechanical and Aerospace Engineering. And this webinar is part of the visiting stay of Mike here in our department, and will be one out of two.
Mm-hmm.
The first one, I think, more theoretical, and the second one more focused on various methodologies.
Sí, sí.
And this one will not be live, unluckily, but we will record both the presentation and the question and answer, so it will be hopefully useful for many others who will see the recording. I'm not wasting more time here, and I'll leave the floor to Mike. Welcome.
Great, thank you. So again, my name is Mike Rayo. I'm an associate professor in industrial and systems engineering at Ohio State. I'm also the director of the Cognitive Systems Engineering Laboratory. Like Riccardo said, this will be a series of 2 lectures, one this week, one next week. So if you like what you see here, we have another one next week. If you don't like what you see here, next week's is completely different. I promise. So we're going to talk about the basics of resilience engineering. And we're going to try to get past the words. In fact, a lot of times in resilience engineering, the words get us tripped up. Like, no, I thought that you meant resilience, or I thought that you meant reliability, or especially as we talk with our systems engineering colleagues, our industrial engineering colleagues, we get mixed up in the words. So I'm going to try to get past the words and get to the actual concepts behind them. So if I could, I always like to know who I'm talking to. So I'd love to get your name and kind of where you come from in the university. I think I know most of you where you come from, but I'm going to make you say it anyway. But there are a few of you that I don't know quite yet. So Antonio, could you start us off?
Hello, I am Antonio Nakada. I am from Venezuela, but I work as associate professor at University of Mercatorum from the last year. I am mechanical engineer. My background is mechanical engineer. I did my Ph.D. in industrial management engineering, and yeah, my main research is in safety, in optimization of the supply chain, and after industrial process and industrial plants.
Great, thank you so much. And could I get your name and where you're from?
My name is Maria.
Great.
I'm a PhD student at the Sapienza University.
Great, thanks. And what department? In this department or other department?
This department.
Great, thank you so much.
Thank you.
So my name is Antonio Dencola. I'm a research scientist. I'm not a PhD student.
Okay, anymore?
Anymore, of course. And I work at IEA, which is a public research agency in the sector of critical infrastructure protection. My lab in particular.
Lovely, thank you, welcome.
Hello, my name is Elena. I am a researcher here in the Department of Mechanical and Aerospace Engineering. My research group is the research group of Riccardo, and the research topics cover the area of safety, industrial plants, operations management, and so on.
Great, thank you. Per favore.
Hello, my name is Lada. I'm a PhD student of the first year. I'm doing my PhD in the management and industrial engineering, focusing about organizational transformation.
Great, thank you, welcome.
Good morning, my name is Margherita. I'm from this department. I'm a postdoctoral researcher here, and my group of research is the one of Riccardo, so I'm managing some like human-machine interaction and this kind of stuff in operational setting.
Great, great. So even more next week will be good, I think, for you.
Mauro Lombardi. I have an aeronautical engineering background, PhD student of Riccardo in this department.
Great.
Francesco Simona, postdoctoral researcher in the Department of Mechanical Engineering and Aerospace Engineering. And yeah.
Great.
The
Thank you. And I'm not going to ask you to do that again. So I did send some reading ahead of time. So at the risk of alienating anybody, who read the reading? Not so much. Okay. All right. So that's good for me to know. So we're going to start with. We're really going to get into resilience and engineering. And we're going to start with, again, these words. So what is the role? So first, in my school, the industrial and systems engineers sometimes believe that they're not real engineers. I don't know if that happens here, but our industrial engineers sometimes get made fun of. They are insulted by the other engineers as not being real engineers. So my background is actually in chemical engineering as an undergraduate, and then in industrial engineering in all my graduate studies. And so I had to really think about what engineering was so that I could convince them that it really was engineering. So first I want us to think about what's the role of an engineer in making systems reliable. And by the way, what's the goal of reliability? So from those words, and I'll try to move this along as well, but when you hear reliable, what does it mean to you? Because by the end of this, we have to get on the same page. We have to have shared common ground about these words. So when you hear reliable, does that word mean anything specifically to you? If not, I'll tell you what it means for us in the United States. No? See, reliable? So, and the reason I'm asking this, I'll see it, is we have the word, does it work? We have reliable. We have robust. We have resilient. And many times, and there's another one, we have, it's a little bit different, but we have rebound. You go away. You go away. And a lot of times, people use these words identically. Oh, they're the same thing. They're not the same thing. So when we have reliability engineers, what they're trying to do is make sure that the system performs appropriately as often as possible. So they're talking about, they're reducing either downtime. So it really is, the percentage of time that the system is working appropriately. Reliability. Robustness is the ability of the system to withstand the challenges that it's encountering. So withstand. So we think about robust, withstand. We're going to use resilient here as extensibility. And there's a big difference between robustness and resilience in that in both cases, the system continues its performance, but in robustness, it doesn't have to change in any meaningful way. In extensibility, in extending, it absolutely has to. So the way I like to talk about it is the Sphinx and the pyramids in Egypt are quite robust. They're still here. In fact, in this city, when I'm doing this lecture here, I should probably talk about all of the things in Rome that are quite robust. They're still here. But what about the Sphinx's nose? Is it robust? No, it's not here. The cannonball took that right off. It doesn't have the ability to extend. So when we think about what we're doing as systems engineers, we have to think about reliability, robustness, and again, I'll think about that as extensibility. Those are complementary, but they are different. We have different tools, we have different perspectives, we have different techniques to be able to work through all of those things. That didn't do what I thought. Here we go. So as we think about Now, this is the other part of reliability. Reliability also assumes that as engineers, and this is actually true of all of our engineering colleagues as well, that we can we can compartmentalize. We can take that big system and we can make it a bunch of smaller systems to understand them, and then make those a bunch of smaller systems and understand them. So it's impossible to understand, to understand this big system, so we'll understand this little one, and we'll understand this little one. And as I understand this, then we'll put everything back together, and I'll now understand the system. But what we know, that's assuming independence. What we know about complex adaptive systems is that they are not independent. They are interdependent. And so when you break this apart and just study this piece, you lose all of these interdependencies. So when you put them together, you don't really understand the system anymore. So this understanding about reliability, so reliability says, I want 99.9999999% uptime, right? That's how often I want to be working. And and when you decompose it, you say, okay, well, if everything has 99.999%, I put it back together, then it's actually, add some more nines, and that's how reliable my system is. And yet we understand that's not how the systems actually work because of those interdependencies. So let's talk about what is resilience. So we talked about what is reliability. We talked about how it's a bit of a trap. But what is resilience? Oh, Antonio. Did it break? And when I want us to think about resilience, I actually want us to think about it as resilient performance. When it gets into resilience, non funciona? Ah. So when we're thinking about resilience, this has us thinking about nouns. This has us thinking about things. But when we talk about resilience performance, we want to be thinking about that performance. Resilient performance is about what the system does, not what the system is. So again, we're starting again to move away from traditional systems engineering and well, that's not true. Convenient systems engineering and getting into what we really want to go, which is the verbs. So what we know about resilience, and maybe you've heard about resilience, not just in Sapienza, not just in the lab of Riccardo Patriarca, but out in the world, we hear about resilience a lot. And it's everything. It's, resilience is why we get up in the morning. Resilience is how we deal with tragedies. Resilience is all of these different things. But what of those can we start to use in resilience engineering? So I shared a couple. Let's see if some of these work. I'll just share this first one. If it works, it's not going to work. Actually, we're behind anyway. So Katy Perry, the pop singer, sings about resilience. She sings about how these terrible things happen and they break up the world, but out of the world springs these wonderful flowers. That's resilience. More broken. And maybe, just maybe you know this story. Maybe you don't. It's been a while. Anybody a boxing fan? Anybody know the boxing heavyweight of the world, Mike Tyson? It's been a while. Mike Tyson, yeah? Well, little known fact, on one day, about 30 years ago, a man from my hometown, Buster Douglas, knocked out the heavyweight champion of the world after he already was technically knocked out. And they say that he came up from the mat, and he came out swinging, and his mother had died the week before, and he brought all these things together 2 days before. And that's him being resilient. So it's all of these things. Oh, really broken. Totally broken. Oh, there we go. Now, in the United States, resilience also is starting to get a bad reputation. So these are actually two quotes. I'm less interested in having a resilient healthcare system if it still can't diagnose skin cancer on dark skin. Where does equity or quality fit in resilience? And this is an even better one. Resilience is basically suck it up and deal with it. So our organizations are saying, you're resilient. We're going to make it harder for you. You're resilient. We're going to take more from you. So this is the kind of the bad side of resilience. And again, I think none of my videos are going to work. But if any of you have watched the movie Home Alone, yeah, did that make it here? Home Alone. John Candy very famously says, he once left his child at a funeral for an entire day where he had to stare at his grandmother. They forgot about him completely. He was in therapy for 2 years, but he got over it. He's talking now. He's very resilient. So again, we have all of these different conceptualizations of resilience. Now let's talk about resilient engineering. So we talk about the ability to resist, absorb, accommodate, adapt to, transform, recover. You see that again up here. Increase adaptive abilities and strengthen preparedness. So how do I deal with change by changing? So this is the beginning of the definition I like best. Resilient performance, the ability to sustain essential services. Now, what's essential? Non so. But it's the ability to sustain those essential services in the face of ever-growing dynamics and uncertainty. So I messed with it a little bit. I added my own. I adapted. I wanted to be clear that it's the ability to adapt. It's not just to sustain, but it's to adapt in order to sustain essential services. And by the way, it's not just that. Let's talk about what those services are. So I need to adapt, and I actually need to potentially adapt my goals, my structures, my functions in order to sustain the more essential goals, structures, and functions. So actually, the first time I put this definition up, my Ph.D. advisor was sitting in the audience of a conference. She came up to the microphone and looked at me and said, I fundamentally disagree with your definition. As I'm in this big room, I was like, oh, that hurts. But what it had me start thinking about is this paradox that we need to change and adapt some things in order to sustain some things. So yes, we need to change in order to sustain. That's the big thing. We need to adapt in order to sustain. And this is the RE part of what I call the core of resilience engineering. The RE part, revise, redesign, right? It just happens to be the first two letters of resilience as well. But it's all of those things. Replan. You don't just do it once. You're going to do it again and again and again and again. All right, so now let's talk about what's engineering. And I'll go quickly through this. And this was for my students at Ohio State, again, so that they could be convinced that we are really doing engineering here. And by the way, some folks that do resilience engineering probably are not. Probably are not. So I like to talk about the difference between designing and engineering. So you have designing, you're going through a series of technology capabilities. You're understanding work domains. Actually, go this way. And design has these design hypotheses, hunches, and then you have what's useful in context. That's what you're building. You also have this kind of more particular, and designers, especially when I was a designer, they kind of hang out here in the particular, what they're actually looking at. As we get into engineering, we actually pull from a pattern base that's much deeper. We pull from a pattern base that's more grounded in science. It's more abstract. And yet, we still have to make contact with the real world. So we have to still go through these patterns and develop models of the world to get back into this design cycle and be good colleagues to our designers. So a lot of people have put requirements for engineering. What's engineering? These are my favorite 4. These come from David Woods, also at my university. But they don't come from him. They come from a lot of places. As you're thinking about what you're doing as a resilience engineer, or I would submit as any engineer, I would think about these. Are you doing these things? Is our work formally grounded in scientific foundations? Can we go all the way down to the science? Or do we get stuck somewhere in the middle? Something with like things that kind of sound like good ideas. Or do we go all the way to the foundation? Are we always seeking to make our practices, our tools, our techniques, our work more effective and accessible? So we tend to have very expensive toys in engineering, especially in engineering universities. I got to see the wind tunnel downstairs. I saw some race cars as I was walking in. They're not cheap. And those aren't ready, you don't just have wind tunnels floating around all of Rome. We have expensive toys here, but what we're trying to do with those expensive toys is make our practices, continue to make them more accessible to more people. You all are doing that here. At the very least with SECA. How do I bring that to more people? We're going to have an explicit approach to designing and architecting. We are not just scientists. We actually have a design approach, an architecture approach. And the 4th one is probably the most important one, is we're explicitly dealing with the trade-offs, especially dealing with complex systems. One rule is never going to work. One perspective is never going to work. So we have to explicitly deal with those trade-offs to all of these things above. The science in one area is going to look like it conflicts the science in another area. And yet we need to architect a solution that works. So how do we deal with those trade-offs? All of those things together, I submit to you that's what engineering is. Regardless if it's chemical engineering, mechanical engineering, aerospace engineering, industrial engineering, resilience engineering, or any of the rest of them. So the way I like to think about what's our process, actually I'm going to skip ahead a little bit. What we like to think about is this is a very abstract process, simplified. But so we like to think about events or issues. So in our research, these are the things we want to solve. And then we're going to develop those into patterns. What are patterns of issues that we see? So if you say, I've seen this before, it doesn't look quite like that, but I've seen this before. This is a workload bottleneck issue, or this is a data overload issue, or what have you. So I go through this analysis, I've done my research, I've seen what's going on in the world, I've analyzed it, I've attached it to issue patterns. I then, from my issue patterns, I see, I have a series of design patterns that I can apply to those issue patterns. Then I have designs, I put those designs in the world, and then I go around the circle again. So this is an engineering process, and it's the one that I use. This is where it gets a little squishy. Squishy, yeah, squishy. That we don't have laws, or they don't look like laws from some of our engineering colleagues, but all of them are going to be patterns. So a way that we can take all of the things that we see out in the world, aggregate those into a pattern, and be able to use that pattern to understand something more about the world. So what's a pattern? First, it's a description and an organization of similarities in abstract of the things that are different in detail. So actually, my grandmother loved to sew. And so I saw these patterns around our house always. And so when you're making this pattern of a dress, it could be different fabric, it could be different colors, it could potentially even be different sizes, but this is the pattern of a dress. So as I saw a dress, I know that the arms go here, I know that the legs go there, or something like that. I know that the head goes here. I don't know very much about dresses, it turns out. So we can have these patterns about these things that we work on as well. And when we talk about these patterns, it's going to capture relationships as well. The other thing that it does, as it's capturing the relationships, it's going to evoke more than the constituents. It's going to bring more to us than just the things that we can see. So this is this is a good example for some and not for others. But so as we look at these, this component and this component, I put them together and I actually see, even though this is still composed of these two things, I actually see a closed object. I see a different pattern. As I put these two things together, I actually don't see those two things. I see a folded horizontal surface. So when I see this thing, I go out in the world and I see workers working. In fact, this happened to me. We were looking at data visualizations of a patient in a hospital, and I saw, and I'll show you in a moment, I saw gobbledygook. I saw, whoa, I don't know what I'm seeing. And the physician that was with me saw all those constituents, and she saw the pattern. That patient's sleeping. That was from all those, she saw the pattern of patients sleeping. So now you get to do it. You get to do one. You get to be just like me, standing next to that physician. Because why do we use these patterns? Frankly, we're hardwired for them, but we need to know the pattern first. Once we know the pattern, it directs us where to look next, what's important, and directs us to related patterns. So, you're in the hospital, you're standing next to the physician, you're walking, and maybe they go to get a coffee, and you're standing there, and these are your two patients. Do you know which one to run to? Huh? So you'd run to the bottom one? Okay. We have a brave soul who'd run to the bottom one. Anybody else who would run to the bottom one? Yeah, run to the bottom one. Anybody who would run to the top one? So again, I'm assuming no trained physicians out here. But to a trained physician, they know exactly who to run to because this is a normal Simon's rhythm. And this is atrial fibrillation. Nice work. Nice work. Nice work. But again, so they see that pattern. So another pattern. So what are we doing as resilience engineers? We're using our training. We're getting out in the world. We're starting to train our new set of eyes. It looks like two of us maybe don't need it. But for the rest of us, we have to train this new set of eyes. We have to learn and master new concepts and new patterns. And we have to start seeing, when I see something out in the world, does it look like a stretch pattern that the system is actively adapting or not? Does this look like an edge pattern? Does it look like it's getting close to the edge of its performance, like it's about to break or not? So I was talking with Francesco yesterday, and he showed me a graph of a power plant. Let's see. So we're going to write all over this thing again. And he showed me something like this graph. Close? Yeah. Close. So we know, so as we talked about those different resilience concepts, for sure, this looks like rebound. Yeah? It's going along. I mean, it's kind of noisy, little noisy. It's going along. Something real bad happens. Then something really good happens. And then whoop, we overshoot a little bit and we come back to noisy but normal. So let's say this is normal here. Rebound. I came back. My question to you is this a pattern of robustness or is it a pattern of extensibility? Second one? Yeah. Second one? Robustness, extensibility? Both? Neither? Extensibility? Margarita? Extensibility? Manuel? Robustness? We have strong. Strong. Francesco? We don't know. We don't know. What we would need to see here, and this should direct our exploration, say, I don't know. And at the end of the day, to the operators, they don't care. They got back. But as resilience engineers and trying to look for the future, we do care because we need to know what kind of changes happened here and what kind of changes happened there. And this visualization doesn't give us that, so we have to go find it some other way. Yeah. This is another example of this. This is called the Cushing pattern. And the Cushing pattern is a pattern where blood pressure goes critically high and heart rate goes critically low. Now, normal physiology, this doesn't happen. It tends to be when your heart rate increases, your blood pressure also increases. But in this case, when you have increasing intracranial pressure, which is real bad, usually much worse than just the blood pressure or the heart. My head is starting to pressurize. That's not good. Is the time where you see this very strange pattern. And what we noticed when we interviewed and did observations with physicians is many of them didn't see the pattern at all, and they just started treating both of those individual symptoms. They said, oh my gosh, I have to treat the critically high blood pressure, and I have to treat the depressed pulse rate. And when you do that, you're risking the life of the patient, because what you're not treating is their head, which is what you need to be treating. So when you see this pattern, again, is this gobbledygook, or do you actually see the pattern out of it? That's absolutely dependent on what eyes you have. If you see this, you're like, yep, I see the Cushingoid pattern here. I'm going to go get a specialist. I'm going to go treat this patient very differently because of the patterns that I saw. I'm going to skip that one. So on the other side, why do we use patterns? It's to disconfirm or deprioritize unlikely claims. So let's talk about the myth of rebound. And I have a long version of this. I can go 3 days on this, but I'll give you the short version. And the short version is, we can never get back to where we were before. We shouldn't expect that we can get back to where we were before. If we have a massive disturbance, rebounding, yes, we want to sustain performance. Yes, we want to get back to performance levels where we were before. But we have to assume that we can't go back in time to that place. So we have to be thinking about extensibility. Let's talk about the limits of robustness. So if I'm not changing, if my system is not changing, no matter what I designed it to do, there will be limits. The world will bring us challenges that exceed those limits. So robustness by itself, again, the ability to withstand, will always be limited. And so if we really care, if it's a high criticality system, robustness will never be enough. We have to have adaptability in that system. And last, and this one is particularly controversial and incendiary in my department, because I have colleagues that have spent their life around optimality. Optimality. We have to talk about the questionable assumptions behind reliability and optimality. So optimality is maximizing my system's performance relative to one or a few measures, right? But what we see with optimality is what actually happens, and are you familiar with Alberto Giacometti? See? I love his work. What actually happens with optimality is a taking. That's what actually is happening in there. So when we're optimal, we'll do more with less. We'll keep taking. We'll keep pinching. We'll keep removing. We'll keep getting more elegant, more streamlined. But we just keep taking and taking. That's what actually happens with optimality. And you see that in bridge building as well. Now, again, should I have shown you a Roman bridge in Portugal? while I'm here? No. I should have shown you a Roman bridge in Rome. I'm learning. But you see, the same thing is happening. We could have built bridges this exact same way, but we didn't, but we wanted to go further. We wanted to span larger bodies of water. We wanted to do it with less material. And for any of you who know the story of the Tacoma Narrows Bridge, it's a good-looking bridge. And it's a good-looking bridge when it caught a cross breeze, that the state of Washington is pretty famous for. It actually, it's not, it moved like this and completely crumbled. Very dramatic. I have the video. I'm not showing it today. And again, would this bridge ever exhibit that behavior? No. Would not. But as we try to optimize, on one of those dimensions, we lose some of the other dimensions. So I'm going to, again, one quick case study. And for those of you who aren't familiar with blood infusions, I promise they won't get very gory. It'll all be in cartoons. But basically, you have a clinician and you have the patient, and as they're getting their infusion, they're getting liquids into their circulatory system. Basic stuff. And that started with a manual system, syringes, or in the United States we have bags. I've heard in European hospitals it's still mostly syringes, but you have bags. But now we have these infusion pumps. So you have a microprocessor and a computer sitting in the middle. So let's talk about what that really does. So again, where did this start? Well, probably started earlier than this. This is still a pretty modern syringe. But you have these syringes. Now, the first thing that happened was that somebody in the United States said, it's not fun work to sit there with a syringe as a nurse or a physician and stand there, so I'm going to put it in a drip bag and I'm going to let gravity do the work. So the nurse can go do something else. This stayed as a syringe. Then I'm going to put, now the other thing is, this doesn't look very precise. So if I'm optimizing on precision, then I can't get a very, this is based on how many drops come through this piece per minute. And that's how you determine how fast the infusion is going. Same thing with this. This nurse, you can't see them, but they're looking at a clock and they're saying how many cc's of fluid is coming through per minute, and that's how you get your precision. Not very precise. Precise enough to save patients, but not very precise. So a series of innovations come, and we have these new machines. Now you have, they're so successful. Now we have a lot of new machines. This is typically what we see in American hospitals, this mess. What we lose here, so what we optimized for was precision. What we optimized for is efficiency. The people don't have to sit there anymore. What we lose is adaptability, and what we lose is observability. I can see exactly what's happening here. I can see exactly what's happening here. I can see what's happening here. I can't see anything that's happening here. It's all actually happening inside the computer or literally behind the computer. So deal with that. You're a nurse and you're coming in. That is not atypical. That's pretty typical. So again, we're back to this. Now I'm dealing with the microprocessor. I'm not actually working with the patient anymore. I'm working with the computer. It's called an infusion pump. So now we trade issues. So now I'm working with the computer, and what we found was that it's actually pretty easy to operate this. I have a little valve. I turn it on and off. I turn it a little bit more, a little bit less. What can happen here is I'm doing it in a keypad. So I could easily type in 100 rather than 10. Now, if you think about the valve, I can do 3/4 versus 1/2, or maybe 80% versus, but I can't do 10 times. This one I can easily do 10 times. And actually, sometimes the computer does it itself. So they said, all right, we have a new class of error, so we're going to create a new class of software that says, okay, well, you can't do that. You can't do any bad doses. And then we find that nurses override. This is actually my dissertation or my master's research. Nurses override 88% of the times that the computer says, no, you can't do that. So we have yet another problem. So this actually came from bad updating of the computer's library. So these are little computers, and this is almost 20 years ago. So these computers weren't necessarily on the internet with each other. So you had to walk around and update the libraries and said, okay, so we've got it. We'll put them all on the internet, and they'll auto-update, and we won't have these problems, and nurses won't ignore them, and we're good. So again, hopefully you can see we've kept moving our optimization. We've kept moving, and what's happening is complexification. This is getting more and more complex. And so, but this time we're done, right? We're done. The internet has solved it. The libraries are updated. The computer is smarter. So we're good. However, what happens when the computer loses its internet connection? Who's lost their internet connection before? Yeah? Who's lost their internet connection today? Yeah. And United States hospitals, and I'm pretty sure they're this way here as well, we're not designed to carry Wi-Fi. They weren't designed well for that. They especially weren't in the United States. So what happens when this computer loses its Wi-Fi? You want to see? That happens. You want to see it again? That happens. I lose all information about my infusion. And this happens pretty frequently. So immediately after the update for this, we started seeing these in hospitals across the United States. Now it's not off. Actually, is it off? Non so. I don't know. Now, as a designer, you have to think, well, but it's going to fail safe, right? Right? If it's resilient, it's going to fail safe. So what's safe in this case? Turning the infusion off, is that safe? Keeping it running at exactly where it is now, but with so keeping the car moving but closing my eyes while I drive, is that safe? I don't know. I'm in an area of complexity that now the operators, in this case nurses, they cannot deal with at all. So this was fixed. I happened to work for the company that built this pump and was doing this research at the same time. That's a very uncomfortable place to be. So again, as you think about this idea of optimization, optimization comes with complexification. Optimization comes with brittleness. Again, this is a pattern. Does it absolutely have to happen this way? No. Does it almost always happen this way? Yes. So that when you're on a project, when you're seeing something like, we have the solution, optimization, you as a resilience engineer, first put on your helmet and then tell them that they're wrong. Because if you're in a safety critical industry, these are the kinds of things that will happen when you're on a hard path towards optimization. All right. We still have time. We still have time together. So I wanted to introduce you to some of the patterns. So again, we talked about issue patterns. What are the villains in our play? These are the three big ones. These are the three patterns of adaptive breakdown. One is decompensation. I'll talk about that. The second one is working at cross purposes. We'll talk about that. The third one is getting stuck in outdated behaviors. If you all would like, during our discussion, we can talk about that one too, but I'll talk more about the first two. Let's talk about decompensation first. So I'm assuming most, if all of you, have at least a rudimentary kind of control theory background, or kind of understand about control. This will be very rudimentary. We're just saying that we have a system. We are trying to operate in this target range. We have challenges that are trying to get us out of that target range. So if we want to use an example, maybe the thermostat. It seems like the target range for thermostats here in Rome is about 5 to 10 degrees warmer than we tend to set them. At least my parents tend to set theirs. So maybe we have a different target. So we're constantly controlling. We're trying to mitigate the disturbances. We're trying to keep it in this target range. Good so far? So we know that those disturbances are going to get stronger and weaker. We're going to have different control. But what we see is if the disturbance, so this is compensation. So again, stronger disturbance met with stronger compensation. Maybe we're starting to move out of the target, so we go even stronger. But eventually, with these new disturbances arise, they grow, they cascade, and eventually they overrun our control. We have reached saturation. We have no more control capacity. So what's our countermeasure? This is our antidote. So again, issue pattern, decompensation. This is a big one. You're going to see it everywhere. Countermeasure, anticipation. Because if I wait till here to exert strong control, I actually don't have enough left. But if I can anticipate these stronger challenges earlier, then I can probably, I have a better chance of staving them off. So there's actually an example. Oh, sorry. I'm skipping over these, or I'm going to go very quickly through these, but these are the 4 potentials of resilience. This is Eric Hollnagel's work. This idea that a resilient organization is learning, is responding, is monitoring and anticipating. But what I want to call out here is, all my stuff is, maybe I can get over there. Is we get in this loop of monitoring our system, and that monitoring influences what you can anticipate. And then your anticipating influences what you're going to monitor. So we're going to continue into this loop. So we actually saw this in Taiwan. We saw, in fact, the entire Taiwanese hospital system had to respond to a dust explosion. And that dust explosion was at an amusement park. It ended up 500 Taiwanese young adults were badly burned and ended up in one or more of the Taiwanese hospitals in Taipei. And again, I'm going to walk us through that. So, like any mass casualty event, at first, we don't know how bad it's going to be. So, and I'll call out to you, and this is all, if you're interested in this, I can send you all the paper on this. This particular hospital, its emergency department, its capacity was at 28. So you'll note that total patients, this is the beginning of this, before any burn patients come to the emergency department, they're already at 40. By the way, 40 more than 28. They typically get 55 in an emergency department whose capacity is 28. So we're already beyond capacity. And this is pretty typical. I haven't been in an emergency department here in Rome. I hope to not go to an emergency department here in Rome. But if I did, I would not be surprised if their capacity, if they were above capacity as well. That's just typically how they run. So you start to see, oh, my patients are climbing a little bit, but still early. What do I do? So what they did was they said, well, there are 3 types of resources that I'm going to need. Again, they're not waiting until, because it's possible that this is going to go up, and then, this is just a couple people that came in. It's going to go down. Everything's going to be fine. No problems. That's not what they thought was going to happen. So they recruited more clinicians. They grabbed a ton of supplies, and they started reconfiguring their hospital right away. They started making chairs into beds. So not exactly, but they started putting patients in beds. They ran out of beds. They said, those chairs are going to be patient beds. They started bringing in stretchers from ambulances. They started putting those in rooms. Those were new rooms. Those were new beds. They started doing all this, but they didn't do it all when they got to here. Or when they got to here, well, I'm already down. Or when they got to here. So again, this is 87 patients in the ED. Capacity is 28. So we're at 3 times capacity. They didn't wait until then. And they didn't Now, they also didn't just slow down here, although they started to see their capacity, the patient load go down. They started bringing those things, each one of these, and I have all of the details there, each one of these is an adaptation that they made. And you notice they didn't wait till here. They started right away. They started calling everybody. They actually was over the radio stations. They called every clinician in. And even folks that weren't called in, when they heard about this dust explosion, they said, I need to go in. They started doing different types of, so all of this stuff very early. So they didn't wait till here. And if they would have waited until here, they would have been too late. And these patients, there probably wouldn't have been more patients, but they would have been sicker patients. They would have been more critical patients, which meant more work. So this is a story of resilient performance. This is a story of extensibility. All right. So that's the first half. A little over the first half. So before I get into, again, I like to talk about the core, the CO and the RE of resilient performance. We just talked about the RE. How do I change? How do I adapt? How do I do the re things? And if any of you would like to work with me to figure out, because this is very English specific, if you want to figure out like what's the snappy, catchy way that we can do this in Italian, happy to work with you about that. Before we get into the co, which I'll explain what that means, and do you have any questions for me about the re? Any questions that we've gone over so far? Anything that you'd like to discuss? Yes?
Yeah, some questions about the patterns.
Okay.
Very interesting, also because I have a computer science background, and many patterns have been developed so far. For instance, there are also ontology design patterns to model situations.
Absolutely.
And so the first question is about where to apply the patterns, because I see patterns to model the current behavior of a system.
Yep.
But also patterns to model how the system should be reengineered. And my question is, are there repositories of existing patterns available to be used? And the second question is about something that is inspired, a question that is inspired by the use of large language models, because one of the criticisms about large language models is that they model the existing, what is already existing.
Right.
They are not able to model something new. And in my opinion, this could be also applied to patterns, because patterns are developed and designed to model something that exists, but not something that could exist. So, and,
absolutely.
So probably we need also in resilience engineering an ability to define new patterns. So maybe something that can facilitate the designing and developing of patterns.
Yeah. So you're absolutely right. So patterns are a way of us using the past to help us understand the present and give us some sense of what could happen in the future. That force of how to, when do I need new patterns, that's all with people right now. So we actually know that if I have this pattern, say this is, one of our patterns is the law of fluency. The law of fluency states that the real difficulties of work in a complex adaptive system are hidden because people are good at doing their jobs. So when you're good at doing your job, the complexity of all the things that you're doing is actually usually even hidden from you. So we have the law of fluency. And then I have that pattern in my head, or I've gone through my catalog of patterns and I found it in the book, chapter 6. And then I go out in the world. I have this in my head. I go out in the world and I see this thing. And the question is, one, does the law of fluency still apply here? Now, it's a law of resilience engineering because it's been tested a lot. So probably what I see here is like, yep, I see that same thing. Maybe I can elaborate this a little bit, but it's still basically the same thing. Now, but I might see this new work system that says the law of fluency doesn't apply here. Again, probably a bad example. But so as I'm doing this, I'm not just going to elaborate. I'm going to create a whole new law, a whole new pattern that maybe is complementary with that pattern, but this is the new one. And now I have something new in my pattern library. So we know that people do this. We know that LLMs don't do this. Could they be designed to do that? Possibly. So I think the value of the patterns is, and by the way, if it's a different pattern and I'm clinging to this pattern, then I may not be able to see this new thing that's happening because I'm so stuck in this pattern. Like optimization. Optimization is a pattern. Reliability is a pattern. I can get so stuck in that pattern. And I suppose extensibility is also a pattern I can get stuck in. That I'm always looking, this is, the answer to this is extensibility. The answer to this is reliability. The answer to this is robustness. I can get stuck here. So this is called fixation. If I shouldn't be stuck there, but I am stuck there, I'm fixated on this pattern. And this is called, if I'm constantly trying to find something new, then we call that vagabonding. That I really could have used that pattern, should have used that pattern, but man, I wanted to go see what was on the other side of that mountain, so I'm continuously looking for new things. I'm never getting back down, grounded in the patterns I know. So yeah, I think, so the patterns themselves are quite flexible. How we use them, I think, is very important. It's a great question. Thank you. Anything else about RE before we get into CO? So as we get into CO, just like RE, revise, replan, we get into CO as well. Or doing things jointly, coordinate, collaborate, co-design, co-plan. We need to do things together. Now, I don't know which is more controversial, the RE side of resilience engineering or the CO side of resilience engineering, but as you bring up LLMs, it's a good example. Most of our colleagues in computer science are not thinking about what we call joint activity. Ooh. They're not thinking about that. They're thinking about how well can my LLM work by itself. They're thinking how well can this individual component work by itself. So let's talk about why that's not going to work. And we'll talk more about that next week as well. So for whatever reason, I decided on a slightly different definition of resilience engineering. Again, continuing operations or delivering essential services when dealing with expected and unexpected situations. This is one that's a little bit closer. In fact, this is the one we saw before. So I'm just sharing the very small taste of the theory of graceful extensibility. Who in the room has read Theory of Graceful Extensibility? How many times? You can show me with your fingers. How many times have you read it? Once? 5? 5? I have to get to my toes. 24? It's a big thing. So when I teach resilience engineering, I have my students read parts of it and actually reformulate it into words that they can understand. This is one of those examples. So basically the theory of graceful extensibility covers a lot of the things that we've already covered. Managing risks of saturation. How do we try to stave off decompensation. Networks of adaptive units. This is where we get into the CO, as well as some of up here. So we're going to really focus on now. So now this is Eric Hollnagel's formulation of the patterns of the cornerstones or the potentials. But we need to add a little bit here. So we added that. We actually, I don't know if my orange is showing up very well. All of these are joint activities. Responding doesn't happen by one component. It's a joint activity. And what I mean by that is that it's working together. And when that group working together isn't working, then I got to go grab some more. I have to recruit to larger parts of my organization, maybe to another organization, maybe to multiple organizations. As the challenge gets bigger, the requirement for jointness goes up. So all of these are joint. So now as we get bigger, we have a problem because we're more likely to work at cross purposes. So hopefully that makes sense. So if I'm getting bigger, if I'm doing something by myself, it's very difficult, although I've done it before, for me to work at cross purposes with myself. That's difficult. Again, a challenge that I accept, but difficult. As I work, if it's Antonio and me working together, we could be getting in each other's way. We could work at cross purposes. If it was the whole room, if it was all of this building, if it was all of Sapienza, if it was the entirety of Rome, it's likely that we could be working at cross purposes. So yes, we need that jointness, but that coordination is really important. And coordination is really important, not just that we're working interpersonally together, but that there are built systems around us that allow us to coordinate. So I wanted to share an example of that, and that should be where we leave it today, and we can have more conversation. All right, so Columbus, Ohio, that's where I live. Columbus, Ohio, one of its benefits is that it's very easy to live there. We don't have hurricanes because we're nowhere near a big body of water. We don't have earthquakes. It's not often too hot, although right now it's actually hotter than it is in Rome. My son just informed me of that. It's not too cold. It's very easy. And in fact, one of the things that Ohio gets, or the Midwest of the United States, actually gets quite a few of are tornadoes. Are you familiar with tornadoes? That word comes through, right? Now, they don't tend, for whatever reason, they don't tend to come into Columbus. They tend to go, the bad weather tends to come right up to Columbus and go right around it. I don't know why. I think it's the heat of the city. That's what I've been told. But sometimes we get tornadoes. So on one morning, on February 28th, there's a warning system that all people at my university get. We all get it through our phones. It's the Buckeye Alert warning system. And we all got this warning that there was a tornado warning, and that means that a tornado had touched down somewhere around Franklin County. So that's how we all woke up at 5:16 a.m. All of our phones went bananas. So here's the timeline. So our National Weather Service issues the tornado watch. Everybody's phones go crazy across all 60,000 students at Ohio State and all 60,000 staff and faculty. All of our phones, next to our beds as we're trying to sleep, all buzzing. The local news coverage goes into action. The weather folks, they love this kind of stuff. Like, they were working in shifts. They're like coming onto the camera, telling about how terrible it was outside, moving on. You could see it all. This is, again, 5:18 a.m. This is where we get this message. 5:15 is the national service. But at 5:45, that tornado watch expires. So this is the story of my university. I also, especially at this time, I also happen to have 2 children in a school system in the same city. And instead of 5:18, we get same kind of system, a warning system. We get our first call at 6:10. So I want you to start envisioning. So again, 5:45, tornado watch is over. Supposedly no damage or no potential damage or no potential hazard in our area. 25 minutes later, the first message goes out to parents not of my university, but parents of children that are in the school system. So this is what we call a lag. Yeah? A pretty significant one. We could call it a lot of other things too. So again, and I talked to my students the next day, like how many of you all got the message? You know, the university students, they all raised their hand. How many of you all just like hit it and went back to sleep? They all raised their hand. How many of you got up in time for class and made it, everything was fine? That's story A. Let's talk about story B. So 6:10, first robocall comes in. Oh, I hope you can hear it. Well, I think maybe not.
Hello.
Oh.
We have an important message from Columbus City Schools. WLNS families, there is a tornado warning for Franklin County. There was a confirmed tornado in West Jefferson a short while ago that is moving east toward Columbus. Please take shelter inside in the lower level if possible. Do not send students to the bus stop. We will advise you as soon as this warning is lifted.
So at 6:10, 25 minutes after the warning was turned off, this message comes to every parent of every child in our school system. Don't send your kids to the bus. Okay, we're not going to send our kids to the bus. So, as any good researcher, I was like, oh, I have something to research. So again, first robocall, I have an unofficial teacher network. By the way, this is the official school network, one message. This is an unofficial teacher network of 6 cluster of teachers that have their phones out. And you see that generated quite a bit of activity. Some before, because they saw this, but quite a bit after, right? They were saying things like, this is before that first robocall. What's the morning look like? I don't know, I'm trying to figure it out. Yeah, I think everyone is. Have we heard from the district? No. I just got an email. Don't send students to the bus stop. And then after, it said, oh my gosh, there's this robocall, but it says stuff's on the west side. The robocall just says that only one school shouldn't send their kids to the bus stop, but they send it to the entire district. So should all of our kids not send our kids to the bus stop? I know it's going to pass, but this isn't so great. This one was probably, this person was channeling their resilience engineering roots. Not a trained resilience engineer, but certainly can kind of feel that. So all these things, could see this confusion. So let's go a little bit further. Now there's this unofficial, coordination network. Now they're starting to get messages from the students on official channels. So they're saying things like, oh, I just got a message. It says don't go to the bus stop. Or wait to go to the bus stop and said, my bus already left. I'm done. So don't go to the bus stop. Wait, my bus already left. We're waiting to hear more. Haven't heard anything. How are we supposed to know when the buses come? Don't know. So these, in this official capacity, these teachers are trying to make sense of this thing, and they're, so hopefully you can start to see that the official communication is absolutely working at cross purposes with the goal of getting students into school. So it goes a little bit further. Now we have a second official robocall. It sounded like this.
Good morning. This is an important message from Columbus City Schools. The district and schools are open today and running on a normal schedule. We understand there is debris down in some areas, and this is causing some delays for certain bus routes by 30 to 60 minutes. As we all prioritize safety this morning, please know that the well-being of our students and staff is of the utmost importance. Please be safe when you commute to school and work. Thank you.
So did you get all that? School is starting on time. On time. This came out at 6:59 a.m. School starts at 7:30. Don't send your kid to the bus stop. 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 School starting in a half an hour. On buses that we don't know where they are. But go. So this comes out at 6:59 a.m. So I want you to think about what goals and functions were preserved here and what were sacrificed. So what goals, again, let's get our resilience engineering hats on. Now let's put and you put yourself in the school district's point of view. What goal was preserved? Yeah. Was it? Was starting school on time preserved for most of the students in the school?
Not for the students, but for the CCS itself.
So somebody got to start school on time, maybe some administrator somewhere. So, but I would say that, so sacrificed on time. I would say that was sacrificed for most students. What goal was preserved? So the good news, yes, please, Francesca.
No one would have been hurt by the...
Exactly. No injuries. No injuries. That's a big one. And that's the goal that won the day. No injuries. Right? No injuries?
I mean, is that really true, though? Because they sent out all that stuff after the tornado had already passed.
Well, I'm just...
It's guaranteed to be no injuries. It
Well,
was done.
well, I'm not saying it was right. I'm saying that goal was preserved.
And they had to do 0 things to ensure that goal.
That's right. That's absolutely right. That's absolutely right. Did they need to prioritize this and sacrifice this? Nah, I would say no. Ultimately, again, as you look at the timeline, they didn't do any of these things at all. So in the service of that goal, and I'm guessing, I did not talk to the administrators here, but in the service of this goal, they put all of this churn in the communication. Now, there's another goal of learning that we don't have up on the board. Oh, I just gave it to you, sorry. There's another goal of school.
Learning did not happen.
That's right. That's right. What was sacrificed on this day? Learning. Absolutely, categorically. And how do we know? Because they told us. What happened? There's supposed to be 40 kids in my first class of the day. There were 12. How does learning happen when they're not there yet? So you can't see this because of my thing, but it says, this is actually from a student at 8:31 a.m. Oh, I can move it maybe like this?
Yeah.
Perfect. This is literally, this is the teacher perspective, and this is the student perspective. Yup, I'm learning nothing. Ha ha. Ha ha ha. So, what questions do you have for me? What do you want to discuss? What still doesn't make sense? Everything made sense. We've solved all the world's problems. You have nothing else. All right, well, so at least for Riccardo students, please email me the questions that you want me to tell him that you asked, because that's what he's going to ask me. Nothing? Says, okay, I have time. I can wait. Did I write it correctly? See?